Okay, moving on to our next example. The ratio of consecutive Fibonacci numbers, f of n plus 1 divided by f of n, converges to a constant value as n increases. Write a script that computes a vector with the first n elements of a Fibonacci sequence, assuming that the variable n is defined, and then computes a new vector that contains the ratios of consecutive Fibonacci numbers. Plot this vector to see if it seems to converge. What value does it converge on? And then there's a note that running the vector seems to converge on a value of negative 1.618. Okay, so here we are in MATLAB, and so we want to create a script that computes the first n elements of a Fibonacci sequence, then also computes the ratio or vector that contains the ratio of the Fibonacci numbers, consecutive Fibonacci numbers. And then we want to plot that ratio and see if it converges on a constant value. Okay. So let's do it. So we're going to start a new script. So we will compute the first n elements of the Fibonacci sequence along with their ratio, and then plots the ratio. So in terms of precondition, n, the number of Fibonacci numbers. In terms of postcondition, then, we'll have, let's use a vector f, vector containing Fibonacci numbers. We'll also have, say, fib ratio, maybe just f ratio, vector containing ratio of Fibonacci numbers. Okay, excellent. Okay. Great. So the first thing I will do is, since I know that the ultimate size of f and f ratio will be of length n, let me just go ahead and presize those. So I'll presize them as, so let's presize our vectors using zeros. So f is zeros, 1 comma n. Let me suppress that output. F ratio is zeros, 1 comma n. Okay. Next, we can initialize our Fibonacci sequence. Okay, so how we'll do that is the first two elements, so f1 is equal to 1 and f2 are both equal to 1. Okay, great. In terms of initializing our fib ratio, well, we could do all of this in a number of ways, but I guess let's start easy. So let's also initialize our fib ratio. Well, so if I were to initialize my fib ratio, what I'm looking at is I'm looking at the ratio of consecutive Fibonacci numbers. So that could be, f2 divided by f1, f3 divided by f2, and so on and so forth. So in terms of that ith value, which in theory would be, say, f1 divided by f0, it doesn't exist. So I'd probably want to stick a value of 0 in there. I won't do that just because I've already initialized it as containing zeros, so we'll just start with the second element. Okay. All right, so let's go ahead and let's do it. Okay. So in terms of calculating these Fibonacci numbers, I know that I will want to loop over this vector f. Okay, so let's do 4. So in terms of which, the first element of the Fibonacci sequence I'm going to be computing will be the third, right? So f3 will be equal to f1 plus f2. So let's start with I is equal to 3, and we can always tweak this up to n. Okay. So compute ith element of, so to compute the ith element of the Fibonacci sequence, it would be f of I is equal to the sum of the previous two elements. So it would be f of I minus 1 plus f of I minus 2. Okay, so it's important that I begins with 3, so that here, when I have 3 minus 1 and 3 minus 2, right, this is 1, they're valid indices. If I had set i's, the lower bound of I being 1, and then wrote the equation as we've seen it before, I'd get an out of bounds error, right? And we can do that just for fun. Let's do that just for fun. Okay, so let's display the value of f. So if I were to compute the first 10 elements of my Fibonacci sequence, so n is 10. Oh, I need to save this. So let's ultimately call this a fib ratio. So if I were to run this fib ratio, it'll display the value of f. There's my first two elements, and then there's the first 10 elements of my Fibonacci sequence. So 10th element's 55. That agrees with what we did back in chapter 3. Okay, so excellent. And so to see what I mean, if I change that to 1, since we're used to starting our loops at a value of 1, right, I get an error, and it tells me where the error occurs. And what's happening is here I have I, which initially is 1 minus 1. That would correspond to an index of 0, which is out of bounds. Okay, cool. Okay. So far, so good? All right, and so if we wanted to calculate the elements of the Fibonacci ratio, or to calculate our fib ratios, we could start simpler, I guess you could say, and we could create another for loop. And the first element, or first value in that sequence we will compute is the second. So remember, the first element would be, say, the first element divided by the 0th element, but there's no such thing as a 0th element. We start with the second element, which would be f2 divided by f1. Okay, so start with 2 to n. It would go all the way up to n, because the nth element would be n divided by n minus 1. And we would have that f ratio of I is equal to f of I divided by f of I minus 1. Cool. Okay, let's keep 10 as it is. We're going to print both of these, and then we're going to play with our code a little bit. So I compute fib ratio. There's f. There's my ratio of Fibonacci numbers. Again, f of 1 is 0. We initialized everything with a value of 0, and so that's that same value. Okay. I suppose we could shift everything, but it's just the same. Okay, so let's see. Let's see if we can figure out, instead of having 2 loops, right? So I'm looping all the way up to n. Is there just a way where I could combine this calculation of fib ratios with this loop somehow? Okay. And there should be, right? If I look at these two, the only difference is here I start with I is equal to 3. Here I start with I equals 2. Okay, so if I just come up here and I compute, say, the second element of f ratio, so it'd be f ratio 2 is f2 divided by f1. Okay, I don't need an element-wise operation because these are two scalar quantities, since I'm just pointing to a particular element. So if I essentially, at first perform the first calculation when I is equal to 2, the first loop iteration, I can then paste that up there and combine them into a single for loop. Okay, in theory, This should be more efficient since I'm just looping once. But when it comes to clarity, let's run this. We'll see that you get the both answer or same answer with each case. So you could ultimately think of it as a matter of preference, whatever would be easier for you to picture or visualize. But in theory, this would be make your code a little more compact, and in theory would be more efficient. Okay. So now we have F and F ratio. Let's go ahead and let's plot it. Okay. So let's start by calculating fib ratio, or plotting it. So if we just plot F ratio, okay, it'll plot the ith element of fib ratio versus the corresponding value of I. Well, so it'll plot the value, each value of that vector versus the corresponding index. And maybe I want to plot these as red circles so I can see them since they're discrete points. Okay, so I'm just going to run it as we build it up to see if it works. There's fib ratio. Already at 10, it looks like it's converging. And in the problem statement, it's suggested a value of about 1.6. Okay. And to check convergence, we could go crazy since I'm not outputting anything right now. I could make n of 1,000. And then if I run fib ratio, I can go all the way to 1,000, and oh yeah, it certainly looks converged. Maybe that's a little too extreme, but nonetheless. Okay, so let's build up this graph and make it look pretty now. And how about as a challenge, just to have fun, let's also plot the Fibonacci numbers on a separate plot, and they'll give us practice playing with the figure command as well. Okay, so if I want to plot my first figure window, this fib ratio, which would be figure 1, plot, and then if I want to add titles, X label would be ratio of consecutive Fibonacci numbers. Okay, cool. Well, the Y label would actually be the ratio. The X label would be the index. Okay, great. And then if on figure 2, so in a second figure, I want to plot Fibonacci numbers, I would plot F. Maybe I do that. I can also do that as red circles. It's just the same. So this would be my index. Y label would be my Fibonacci number. Okay, so let's save, and let's see if we have this working correctly. So there's figure 1, hey, and there's figure 2. So now I have a plot of Fibonacci ratio, and then here's my corresponding Fibonacci number. So it looks a little unclear with 1,000. Let's change it to 100 and see if that's better. Okay. Alright, so it looks a little better. It's just the Fibonacci sequence is really taking off. But cool, now we have 2 plots, and if we want to save both of those figures, we can do that. Okay, and so I should point out the key with having multiple figures is here I open up figure 1, I open up my first figure window, I do everything I want within that figure window, and then I go and I open up another figure window and do whatever I want separately in that figure window. And if I want to switch back, I'd have to do a figure 1 again, or vice versa. Okay. So let's save this fig. Okay, this will be fib ratio plot. Okay, .fig. And if I want to print a copy from my report, say print. We keep doing a PNG. We can do a PNG again. Okay. If I want to do that again here, copy and paste and just update. So this would be maybe just fib plot. Cool. So if I save this and run it, now I have my two beautiful plots, and now I have two beautiful PNGs. I'm going to open it outside of MATLAB. Some nice pretty figures that I could include in, say, a report, or maybe you want to print them out and post them on your refrigerator. Okay, so that is it. That's the problem. We turned it into pretty nice result.